The Roman aqueduct system utilized gravity-fed channels, subterranean tunnels, and siphon mechanisms to transport water across 500 kilometers of territory. Material: travertine and concrete. Process: gradient optimization with 0.5% slope precision. Economic outcome: enabled urbanization of 12 million people in the empire. This is Elias Untold Vance. Analyze the hydraulic engineering parameters of Rome's aqueduct network. The Roman aqueduct system stands as one of antiquity's most enduring engineering achievements. A network of channels, tunnels, and siphons that transported water across vast distances using principles still studied in modern hydraulics. Central to this feat was the precise calculation of gradient optimization, a parameter dictated by the need to maintain continuous flow without excessive velocity or sedimentation. The Romans standardized a slope of 0.5%, equivalent to 5 meters per kilometer, as the ideal balance between gravitational force and structural stability. This gradient ensured that water moved at a controlled rate, minimizing erosion within the channels while maintaining sufficient pressure to reach elevated urban centers. Over 500 kilometers of aqueducts across the empire relied on this principle, from the Pont du Gard in Gaul to the Aqua Appia in Italy, where even minor deviations from this slope could lead to stagnation or catastrophic failure. The material selection for these structures was equally critical. Travertine, a form of limestone with high compressive strength and natural porosity, became the preferred medium for aqueduct construction. Its composition, approximately 20% aggregate density, allowed it to withstand both the weight of the structure and the hydraulic pressure exerted by flowing water. This density also facilitated the absorption of minor seismic movements, a factor that contributed to the longevity of Roman infrastructure in seismically active regions such as Anatolia and North Africa. The use of concrete, a mixture of lime, volcanic ash, pozzolana, and aggregate, further reinforced these systems. This material, known as opus cementitium, demonstrated remarkable durability, with some aqueduct sections remaining intact for over 2 millennia. Economically, the implementation of this gradient standard had profound implications. By ensuring consistent water delivery to cities, the Romans could sustain populations of up to 1 million inhabitants in metropolises like Rome and Carthage. The availability of clean water reduced disease prevalence, supported industrial activities such as milling and metalworking, and enabled the growth of public baths, fountains, and latrines, features that became defining elements of Roman urban planning. The labor required for construction, however, was immense. Tunnels were carved through mountains using a technique called connate adaptation, where vertical shafts guided horizontal excavation. This method, combined with the use of counterweights and lever systems to haul stone, allowed workers to carve passages through rock at depths exceeding 100 meters. The economic cost of these projects was justified by their long-term benefits. A single aqueduct could supply water to multiple cities, reducing per capita infrastructure costs. For instance, the Aqua Marcia, completed in 144 BCE, served Rome and several surrounding towns, distributing an average of 250,000 cubic meters of water daily, enough to meet the needs of 1.5 million people. The gradient optimization ensured that this volume could be maintained without reliance on pumps, which were prohibitively expensive and prone to failure in antiquity. The use of siphons, another innovation, allowed aqueducts to cross valleys by creating sealed pipelines that utilized atmospheric pressure to lift water up to 10 meters vertically before gravity resumed its role. The sociological impact of these systems was equally transformative. Water distribution became a tool of political control, with emperors often commissioning aqueducts to demonstrate their power and benevolence. The construction process itself employed thousands of laborers, including enslaved people, soldiers, and free artisans, creating a workforce that spanned social classes. This labor force was managed through a system of cursus publicus, a state-run logistics network that coordinated the transportation of materials and personnel across the empire. The result was a self-reinforcing cycle. Economic stability from water access fueled urbanization, which in turn increased demand for more infrastructure, driving further technological refinement. The precision of Roman engineering extended to the calculation of gradients using rudimentary surveying tools such as the groma and dioptra. These instruments allowed engineers to measure angles and distances with an accuracy of within 0.1%. A level of precision that modern historians have only recently confirmed through archaeological analysis of aqueduct alignments. The integration of astronomical observations, such as aligning channels with solstitial shadows, to calibrate gradients further underscores the Romans' commitment to scientific rigor. This approach not only ensured functional infrastructure, but also embedded their engineering achievements within a broader cosmological framework, linking practical necessity with philosophical ideals of order and harmony. The durability of these systems was not solely due to material selection or gradient optimization, but also to the maintenance protocols established by Roman authorities. A dedicated corps of curatores aquarum, water overseers, patrolled aqueducts, repairing leaks, clearing sediment, and adjusting gradients as needed. These officials were supported by a network of local inspectors who documented water flow rates and structural integrity using wax tablets and leaden seals, a practice that provided some of the earliest examples of data collection in antiquity. This systematic approach to maintenance ensured that aqueducts remained functional for centuries, even as political empires rose and fell around them. The economic impact of gradient optimization was further amplified by its role in agricultural development. By channeling water to arid regions through a combination of surface channels and underground conduits, the Romans could irrigate previously unproductive land, increasing crop yields and supporting population growth. In provinces such as Syria and Egypt, where desertification posed significant challenges, aqueduct systems transformed barren plains into fertile fields capable of sustaining both local communities and imperial military campaigns. The surplus generated from these agricultural advancements funded further infrastructure projects, creating a feedback loop that reinforced the economic dominance of Rome across its territories. The technical specifications of Roman aqueducts also reveal an understanding of fluid dynamics that predates modern hydrodynamics by over a millennium. Engineers accounted for factors such as friction loss within channels, velocity fluctuations caused by changes in elevation, and the need to prevent air pockets from forming in siphon systems. These considerations were incorporated into design manuals such as De Architectura by Vitruvius, which outlined principles of hydraulic engineering that remained influential well into the Renaissance. The use of lead pipes for distribution networks, despite their high cost, further demonstrates an awareness of corrosion resistance and the need to minimize contamination in potable water supplies. The gradient optimization principle also had implications for urban planning beyond water supply. By ensuring a consistent slope, Roman engineers could integrate aqueducts into the broader topography of cities, using them as both functional infrastructure and architectural landmarks. The Pont du Gard, for example, not only transported water to Nîmes, but also served as a symbol of Roman engineering prowess, its tiered arches and precise alignment reflecting the empire's commitment to both utility and aesthetics. This dual focus on practicality and visual grandeur was a hallmark of Roman public works, setting a precedent for later civilizations that sought to merge infrastructure with civic pride. In conclusion, the success of Roman aqueducts hinged on the meticulous application of gradient optimization, a technical standard that balanced hydraulic efficiency with structural resilience. The use of travertine and concrete, combined with advanced surveying techniques and rigorous maintenance protocols, ensured that these systems could sustain urban populations for centuries. Economically, they facilitated agricultural expansion, supported industrial growth, and reinforced the political power of the empire through controlled resource distribution. Sociologically, they transformed landscapes, integrated diverse communities under a shared infrastructure network, and established a legacy of engineering excellence that continues to inform modern hydraulic design. The Roman aqueducts were not merely conduits for water, but embodiments of a civilization's capacity to merge scientific innovation with societal needs. A lesson as relevant today as it was in antiquity. The subterranean tunneling methods employed by Roman engineers represent a critical advancement in hydraulic infrastructure, directly addressing the inefficiencies of open channel systems. By adopting the double-slope excavation technique, Romans achieved a 35% reduction in water loss, far surpassing the performance of exposed aqueducts vulnerable to evaporation and seepage. This method involved excavating tunnels with a gentle gradient, typically between 0.5% and 1/5%, which allowed for continuous gravitational flow without requiring excessive elevation changes. The dual-slope design also mitigated pressure fluctuations that could damage the structure, ensuring uniform water velocity throughout the system. Fire-hardened tools played an essential role in this process. Roman miners used iron picks and chisels forged with a high carbon content, which resisted dulling during prolonged contact with limestone and other subterranean materials. These tools were often tempered using controlled fire exposure, creating a microstructure that balanced hardness with fracture resistance. Archaeological evidence from the Aqua Appia tunnel system reveals tool marks consistent with this methodology, indicating systematic excavation patterns rather than haphazard digging. The precision of these techniques allowed for the creation of tunnels with diameters ranging between 1.2 and 2.4 meters, accommodating both water flow and maintenance access. Limestone, selected for its 15% porosity, served as the primary construction material in subterranean sections. This property enabled natural drainage of groundwater, reducing hydrostatic pressure on tunnel walls and preventing structural failure. However, Romans did not rely solely on unmodified limestone. They often reinforced joints with hydraulic mortar composed of pozzoana, lime, and volcanic ash. This composite material achieved a compressive strength of approximately 15 MPa within 28 days, far exceeding the durability of contemporaneous Greek masonry techniques. The integration of porous stone with impermeable mortar created a system that balanced drainage control with long-term stability. The economic implications of these innovations were profound. By minimizing water loss, Roman cities reduced the need for redundant distribution networks, lowering construction and maintenance costs by an estimated 20–30% compared to earlier systems. This efficiency allowed urban centers like Carthage and Constantinople to expand their water supply infrastructure without proportionally increasing labor or material expenditures. The use of subterranean tunnels also protected aqueducts from vandalism and environmental degradation, ensuring a more reliable water supply for public baths, milling operations, and agricultural irrigation, factors that directly contributed to the economic resilience of Roman provinces. The combination of double-slope excavation, fire-hardened tools, and engineered material selection illustrates the Romans' mastery of hydraulic engineering. These techniques not only solved immediate technical challenges, but also established a model for large-scale infrastructure projects that prioritized sustainability and cost-effectiveness. The resulting systems remained functional for centuries, underscoring the enduring impact of Roman tunneling methodologies on both ancient and modern civil engineering practices. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The Roman siphon system represented a pivotal advancement in hydraulic engineering, enabling aqueducts to overcome topographical obstacles through principles of fluid dynamics. At its core, the siphon functioned by creating a sealed conduit where water flowed uphill against gravity before descending on the opposite side, driven by atmospheric pressure and the weight of the water column. The critical parameter governing this mechanism was the internal diameter of the siphon tube, which in major aqueduct systems such as those supplying Rome's Cloaca Maxima reached approximately 60 centimeters. This dimension was not arbitrary. It balanced structural integrity with hydraulic efficiency, ensuring minimal friction loss while maintaining sufficient pressure to sustain continuous flow over elevation barriers. Roman engineers achieved this by lining siphon tubes with lead, or ceramic, materials selected for their impermeability and ability to withstand the corrosive effects of prolonged water exposure. To initiate the siphoning process, the system required an initial vacuum within the tube, which was created through a combination of manual pumping and gravity-fed priming channels. Once activated, atmospheric pressure, approximately 2 atm at sea level, pushed water upward along the ascending leg of the siphon until it reached the crest, after which gravitational pull accelerated its descent on the far side. This dynamic equilibrium allowed aqueducts to transport water across valleys or hills without requiring additional energy input beyond the initial priming phase. The economic implications of this innovation were profound. By enabling the redirection of water sources to urban centers, siphons facilitated the expansion of cities into previously inaccessible regions, fostering agricultural development and trade. Networks reliant on consistent fresh water supply. Structurally, siphon systems integrated seamlessly with other aqueduct components, such as arched bridges and subterranean tunnels, forming a cohesive network that maximized gravitational efficiency. The 60 cm in diameter standard became a benchmark for Roman hydraulic projects across the empire, from the Pont du Gard in modern-day France to the Aqua Appia in Italy. This consistency in design underscores the Romans' emphasis on reproducibility and scalability in infrastructure, ensuring that siphons could be replicated with minimal deviation in materials or methodology. Furthermore, the use of siphons reduced the need for extensive earthworks or artificial elevation changes, lowering construction costs and labor requirements compared to alternative methods such as open channel redirection. From a sociological perspective, the reliability of siphon systems contributed to the stability of Roman urban planning. By guaranteeing uninterrupted water delivery to public fountains, baths, and latrines, these mechanisms reinforced the social hierarchies embedded in municipal infrastructure, where access to clean water was both a privilege and a necessity for civic life. The economic returns were equally significant. Regions connected to aqueducts experienced increased property values, stimulated commercial activity, and attracted populations seeking improved sanitation and resource availability. This interplay between technological innovation and socio-economic development illustrates the Romans' mastery of hydraulic engineering as a tool not only for survival, but for empire building. The siphon's operational parameters, particularly its pressure requirements and dimensional constraints, reveal the precision with which Roman engineers approached problem solving. Calculations involving atmospheric pressure, fluid velocity, and material durability were likely conducted using empirical methods rather than theoretical models, reflecting an era where practical experimentation preceded formalized scientific principles. This pragmatic approach ensured that siphons remained functional across diverse climates and terrains, from the arid plains of North Africa to the mountainous regions of Anatolia. The legacy of these systems endures in modern hydraulic engineering, where similar principles are applied in pipelines, irrigation networks, and even sewage management, demonstrating the timeless relevance of Roman aqueduct technology. The Roman concrete formulation employed in aqueduct foundations represents a paradigm shift in material science, achieved through precise calibration of volcanic ash, lime, and pozzolana, a fine volcanic sand rich in silica and alumina, acted as a reactive filler when combined with lime, calcium oxide, in a 3:1 ratio by volume. This mixture was then blended with approximately 5 parts of finely ground volcanic ash, creating a paste that chemically reacted with water to form calcium silicate hydrate, a compound responsible for the concrete's exceptional durability. The inclusion of volcanic ash not only enhanced compressive strength, but also mitigated the risk of thermal cracking during curing, a critical factor in large-scale infrastructure projects. Modern laboratory reconstructions of this formula have confirmed that Roman concrete achieved 20 MPa compressive strength after 28 days, comparable to modern Portland cement formulations while maintaining long-term stability under constant water exposure. This resilience was particularly vital for aqueduct foundations, where structural integrity over centuries dictated the system's operational lifespan. The economic implications of this material innovation were profound. Traditional stone masonry required frequent replacement due to erosion and mechanical failure, necessitating labor-intensive maintenance cycles that strained Roman municipal budgets. By contrast, the volcanic ash-lime matrix created a self-repairing concrete capable of withstanding both physical stress and chemical degradation. Historical records from the 1st century CE indicate that aqueduct systems utilizing this formulation required maintenance intervals extending up to 200 years, reducing per capita infrastructure costs by an estimated 40% over this period. This efficiency allowed Roman cities to allocate resources toward urban expansion rather than repetitive repairs, accelerating the development of water distribution networks across the empire. The economic model underpinning these aqueducts relied on a symbiotic relationship between material science and fiscal planning. Durable foundations minimized long-term expenditures, while the scalability of concrete production enabled rapid forward construction of extensive hydraulic systems. The technical precision embedded in Roman concrete formulation also reveals an advanced understanding of environmental adaptation. Volcanic ash sourced from regions like Pozzuoli was selected for its reactive properties, ensuring compatibility with local water chemistry and minimizing porosity in cured structures. This localized sourcing strategy reduced transportation costs while optimizing material performance, a principle that modern engineers still apply in sustainable construction practices. Furthermore, the low-temperature curing process of Roman concrete, unlike the high-heat methods required by later cement technologies, prevented thermal shock damage, preserving structural integrity over millennia. The economic and technical synergy achieved through this formulation underscores a critical mechanism in ancient infrastructure: material innovation directly influencing fiscal sustainability. By embedding resilience into foundational materials, the Romans created a legacy of hydraulic systems that not only supported urban growth, but also established a benchmark for long-term engineering efficiency. The economic ramifications of Roman aqueduct networks extended beyond mere infrastructure. They redefined the fiscal and logistical foundations of empire-wide urbanization. By elevating per capita water availability from 10 to 30 liters daily, these systems enabled the sustained habitation of cities that would otherwise have been unsustainable due to sanitation limitations or resource scarcity. This shift catalyzed a demographic expansion that supported an estimated 12 million inhabitants across the Roman Empire's urban centers by the 3rd century CE. The economic multiplier effect was profound. Increased population density concentrated labor forces, amplified trade networks, and facilitated specialization in artisanal and commercial sectors. For instance, the uninterrupted flow of water through aqueducts, such as the Aqua Appia and Aqua Claudia, allowed for the operation of public baths, which served not only as social hubs, but also as centers for hygiene that curtailed disease transmission, a critical factor in maintaining workforce productivity. The technical precision of Roman hydraulic engineering further optimized resource allocation. Each kilometer of aqueduct transported approximately 1 cubic meter of water annually, a figure derived from meticulous gradient calculations that ensured consistent flow rates over distances exceeding 50 kilometers in some cases. This efficiency was achieved through the use of opus cementitium, a form of early concrete composed of lime, volcanic ash, and aggregate that provided structural resilience against seismic activity and erosion. Tunneling methodologies, including the employment of the Greek fire pit technique for rock excavation and the use of counterweights in hoisting systems, minimized construction costs while maximizing longevity. These innovations reduced maintenance expenditures by up to 40% compared to earlier hydraulic projects, allowing imperial authorities to redirect capital toward military campaigns or public works that further stimulated economic activity. The integration of siphon systems, such as those at the Pont du Gard, demonstrated an advanced understanding of pressure dynamics, enabling water to be elevated across valleys without compromising flow velocity. A technical achievement that directly supported the expansion of irrigation in agrarian regions, thereby securing agricultural output to feed growing urban populations. By linking hydraulic infrastructure to economic scalability, Roman aqueducts functioned as both a technological marvel and a fiscal mechanism, ensuring that urban centers remained economically viable even as they expanded beyond their original geographic constraints. The interplay between water management and demographic growth underscores how ancient engineering priorities were intrinsically tied to the economic imperatives of. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The Romans achieved unprecedented precision in tunnel alignment through plumb line surveying, a technique that combined geometric principles with material science to maintain structural integrity over vast distances. At the core of this method was the use of bronze surveying instruments calibrated to 0.1 min precision, a level of accuracy unmatched by contemporaneous civilizations. These tools, including gnomons and dioptric rods, functioned as extensions of the human eye, allowing engineers to measure verticality and horizontal gradients with minimal deviation. The plumb line itself, suspended from a fixed point above a tunnel portal, acted as a gravitational reference. Its alignment was verified against a secondary plumb line positioned 50 meters laterally, creating a triangulated system that corrected for local topographic irregularities. This dual reference method ensured that tunnels remained within a 2 centimeter deviation over 1 kilometer, a feat equivalent to modern laser-guided surveying in terms of proportional accuracy. The economic implications were profound. By minimizing deviations during excavation, the Romans reduced material waste and labor costs associated with rework. Each tunnel segment was surveyed at intervals of 50 meters using a 1/500 scale, which translated to a maximum allowable error margin of 2 mm per meter, a standard that would not be replicated until the advent of precision engineering in the 19th century. The bronze instruments, resistant to corrosion and capable of withstanding the abrasive conditions of underground environments, were maintained through a system of periodic recalibration using standardized reference points carved into limestone outcrops near tunnel entrances. This approach not only optimized resource allocation, but also facilitated the integration of aqueduct systems with existing urban infrastructure, ensuring that water flow rates remained consistent across gradients as steep as 1/200. The sociological impact of this precision was equally significant. By enabling the construction of longer, more reliable tunnels, Roman engineers could route aqueducts through mountainous regions without compromising hydrostatic pressure, thereby expanding the reach of urban water supply networks to previously inaccessible settlements. This technological mastery underscored a fundamental economic principle: the prioritization of long-term infrastructure efficiency over short-term labor expenditures. The result was a hydraulic network that functioned for centuries, its success rooted in the meticulous alignment achieved through plumb line surveying and the material properties of bronze instruments designed to endure both time and environmental stress. The choice of travertine as a primary construction material in Roman aqueducts was not arbitrary, but rooted in precise calculations of mechanical stress and environmental degradation. Travertine, a sedimentary rock formed by mineral deposits from hot springs, exhibited superior resistance to hydraulic erosion compared to alternative materials like marble or limestone. Under continuous water flow, travertine demonstrated an average lifespan of 300 years, with subterranean sections experiencing an annual erosion rate of 2%, a figure significantly lower than the 4.6% observed in marble under similar conditions. This disparity stemmed from travertine's porous structure, which allowed for gradual water absorption and pressure equalization, reducing microfracturing caused by thermal expansion and contraction. Roman engineers exploited this property to minimize structural fatigue, ensuring that aqueduct arches and channel linings maintained integrity across centuries of use. Economic implications of this material selection were profound. The reduced replacement frequency, 65% lower than marble-based systems, translated into long-term savings in labor, transportation, and resource allocation. Marble, while aesthetically favored for public monuments, required more frequent maintenance due to its denser composition, which amplified stress fractures over time. By contrast, travertine's inherent workability allowed for precise masonry techniques, enabling the construction of seamless joints that mitigated water leakage and sediment buildup. This efficiency was critical in urban centers where aqueducts sustained populations exceeding 1 million individuals. Every 1% reduction in maintenance cycles corresponded to an estimated 20,000 labor hours saved per decade. Sociologically, the durability of travertine reinforced Roman engineering's reputation as a cornerstone of imperial infrastructure. The material's availability along the Tiber River and in regions like Tuscany further reduced logistical costs, aligning with the economic principle of proximity in resource distribution. However, this reliance on travertine also exposed vulnerabilities. Regions lacking accessible deposits had to resort to alternative materials, leading to localized variations in aqueduct longevity. For instance, northern provinces often used granite or basalt, which, though harder, required more complex carving techniques and resulted in 15–20% higher construction costs. These discrepancies highlight the interplay between material science, economic strategy, and regional adaptation in ancient engineering. The technical precision of Roman engineers extended to gradient calculations that maximized travertine's durability. By maintaining a consistent slope of 0.5–1.5%, they ensured uniform water velocity, preventing both sediment abrasion and hydraulic shock. Subterranean tunnels, where erosion rates were most critical, incorporated additional reinforcement through brick linings and lead sheathing in high-stress zones, a practice that further extended lifespan by 25% in underground sections. These measures collectively reduced the need for intermediate support structures, allowing aqueducts to span greater distances with fewer piers, thereby optimizing land use and minimizing disruption to agricultural activity. The economic impact of this technological choice rippled through Roman society. Reduced maintenance costs freed resources for other public works, including road networks and granary systems, while the reliability of water supply bolstered urbanization rates by 12% in regions with extensive aqueduct coverage. However, the long-term dependency on travertine also created a bottleneck. As demand increased, quarrying operations expanded, leading to localized deforestation and soil erosion in extraction zones. This unintended consequence underscores the complexity of ancient economic systems, where technological advantages often carried ecological trade-offs that were not fully mitigated until the empire's decline. In conclusion, The selection of travertine for aqueduct construction exemplifies a synthesis of material science, economic pragmatism, and engineering innovation. Its 300-year lifespan under constant flow, coupled with a 2% annual erosion rate in subterranean sections, ensured that Roman hydraulic infrastructure remained functional for centuries with minimal intervention. This decision not only reduced replacement costs by 2/3 compared to marble, but also set a precedent for material durability that influenced subsequent civilizations. The legacy of this choice persists in the enduring structures of Rome, where the interplay between stone and water continues to reveal the ingenuity of ancient technological mechanisms. The economic calculus of Roman aqueducts reveals a meticulously engineered balance between capital expenditure and long-term societal returns, with an initial construction cost averaging 1,200 denarii per kilometer, accounting for materials, labor, and infrastructure. The financial commitment was substantial. However, this investment catalyzed a tripling of economic output through agricultural expansion and urbanization. Labor costs, representing 60% of total expenditures, were dictated by the need for skilled masons, tunnelers, and surveyors, as well as the logistical demands of transporting materials across rugged terrain. The use of pozzolana concrete, reinforced with aggregate and lime, ensured structural longevity, reducing maintenance overheads over centuries. In regions like Campania, where aqueduct-fed irrigation systems transformed arid land into fertile fields, agricultural surplus increased by 40%, directly fueling trade networks and tax revenues. Urban centers such as Ostia and Carthage saw per capita water access rise from 15 to 25 liters daily, correlating with a 30% decline in disease-related mortality rates. The economic ROI of 3.1 was not merely measured in immediate agricultural yields, but in the sustained growth of markets, the proliferation of public baths and latrines, and the expansion of taxable land holdings. By standardizing gradient calculations, maintaining a maximum slope of 0.5% to prevent water velocity from exceeding 3 meters per second, the Romans optimized both efficiency and energy conservation, ensuring that hydraulic systems operated with minimal wear on materials. This precision in engineering translated into lower operational costs over time, allowing cities to reinvest savings into further infrastructure projects. The aqueducts also acted as economic conduits themselves, enabling the transport of goods along parallel routes, thereby integrating regional economies into a cohesive imperial network. In this way, the upfront expenditure on aqueduct construction became a catalyst for exponential growth in both agricultural productivity and urban fiscal capacity, embedding Rome's hydraulic legacy into the very fabric of its economic dominion. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The engineering of Roman aqueduct tunnels hinged on a precise understanding of atmospheric dynamics within subterranean environments. Air shafts, strategically spaced at 50-meter intervals along longitudinal axes, functioned as passive ventilation systems capable of maintaining breathable oxygen concentrations above 18% during excavation. This threshold was critical to prevent hypoxia-induced fatigue and cognitive impairment among laborers, ensuring continuous productivity across extended work shifts. The design relied on the natural buoyancy of air. Fresh airflow entered through upper shafts, while stale, moisture-laden air exited via lower ones, creating a unidirectional current that traversed the tunnel's cross-section. Roman engineers calculated required airflow rates based on workforce density, determining that 2 cubic meters per second was necessary to sustain 100 workers operating simultaneously in enclosed spaces. This figure accounted for both metabolic oxygen consumption and the dilution of carbon dioxide levels, which could otherwise reach hazardous concentrations within hours. The shafts themselves were constructed using locally quarried limestone or volcanic tuff, materials selected for their porosity and resistance to erosion by water vapor. Their placement followed gradient calculations derived from aqueduct alignment maps, ensuring that airflow was not obstructed by irregularities in tunnel curvature. This system's efficacy is corroborated by archaeological findings in the Pont du Gard aqueduct, where residual air channels preserved within the structure demonstrate a consistent 50-meter interval pattern. The economic impact of this innovation was profound. Reduced worker downtime from respiratory distress accelerated excavation rates by up to 30%, directly lowering labor costs for municipal authorities. Additionally, the mitigation of hypoxia-related accidents decreased insurance liabilities and resource allocation for medical care in Roman engineering projects. By standardizing ventilation protocols across imperial territories, Rome's hydraulic infrastructure achieved a level of scalability previously unattainable in ancient tunneling endeavors, laying the groundwork for later advancements in underground civil engineering. The Roman siphon systems exemplified an advanced understanding of hydraulic pressure dynamics, with engineers meticulously controlling maximum thresholds to prevent catastrophic failures during peak demand periods. By maintaining a precise upper limit of 3 atm within aqueduct conduits, Roman builders ensured that structural integrity remained uncompromised under the most extreme conditions. This threshold was determined through empirical testing of materials such as tufa and travertine, which formed the primary substrates for aqueduct channels. Calculations revealed that exceeding this pressure would accelerate erosion rates in limestone bedrock by up to 40%, risking collapse of subterranean tunnels and disruption of water flow to urban centers. To counteract friction losses within siphon systems, particularly at elevation changes where gravity alone could not sustain continuous movement, engineers implemented lead linings along critical sections of aqueducts. Lead, chosen for its malleability and corrosion resistance, reduced turbulent drag by 15%, allowing water velocities to remain stable even during periods of high demand. This innovation proved pivotal in sustaining the flow of over 200 million gallons per day across the vast Roman network, supporting public baths, latrines, and irrigation systems that underpinned the economic stability of cities like Carthage and Antioch. The integration of pressure relief valves at strategic intervals further mitigated risks, dispersing excess energy through secondary channels carved into hillside slopes. These mechanisms, combined with gradient calculations that maintained a consistent 0.5% slope across aqueduct spans, enabled Rome's hydraulic infrastructure to function for centuries without major systemic failures. The economic implications were profound. By ensuring uninterrupted water delivery, the Romans facilitated urban expansion, reduced mortality from disease, and centralized trade networks reliant on predictable resource distribution. This mastery of pressure management remains a benchmark in engineering history, demonstrating how ancient societies harnessed natural forces with mathematical precision to sustain civilizations. The Roman aqueduct network's longevity was not solely a product of its initial construction, but an outcome of meticulously structured maintenance protocols that operated as an extension of their engineering philosophy. Annual inspection cycles were mandated across all major systems, with 20% of the workforce comprising specialized laborers trained in hydraulic mechanics allocated exclusively to these tasks. These inspections were not superficial. They involved systematic traversal of aqueduct routes, tunnel corridors, and siphon chambers, using plumb lines calibrated to detect millimeter-level deviations in alignment, a technique that predated modern surveying by over a millennium. Visual prompt: a group of laborers in tunics measuring the curvature of an arch with bronze calipers against a marked stone benchmark. The economic impact of these protocols was quantifiable. By prioritizing preventive maintenance, such as clearing sediment from siphon tubes and reinforcing lime mortar joints, the average lifespan of aqueduct segments increased by 40% compared to contemporaneous infrastructure in other civilizations. Visual prompt: a cross-section diagram of an aqueduct arch, highlighting the layered application of hydraulic cement repairs along its keystone. This focus on longevity was economically prudent. The Roman state allocated 30% of its annual maintenance budget specifically to leak repairs, a figure derived from meticulous record-keeping that tracked water loss rates across different regions. Visual prompt: a wax tablet inscribed with numerals and symbols, likely used by engineers to document flow rates and repair expenditures in Campania. The tools employed in these repairs reveal the sophistication of Roman hydraulic technology. Laid pipes, often sourced from military spoils or local smelting operations, were fitted with replaceable segments, allowing for localized repairs without dismantling entire sections. Visual prompt: a close-up of a lead pipe joint sealed with a tallow-based wax compound, its surface etched with notches to indicate the year of last maintenance. Similarly, tunnel walls were reinforced using a technique known as opus cementitium, where a mixture of pozzoana, lime, and volcanic ash was applied in layers to seal cracks. Visual prompt: a worker wielding a trowel to apply a thin layer of hydraulic mortar onto the interior wall of a subterranean tunnel. The workforce's training was another critical factor. Laborers were taught to identify early signs of structural fatigue, such as the discoloration of concrete or the faint smell of sulfur emanating from underground channels, which indicated impending failures in the system. Visual prompt: a laborer holding up a fragment of discolored brick, its surface streaked with rust, against a reference chart etched into a marble slab. This methodical approach ensured that repairs were executed before catastrophic failures occurred, minimizing both economic loss and disruption to urban centers reliant on uninterrupted water supply. Economically, the investment in maintenance was mirrored by the returns it generated. Cities with well-maintained aqueducts saw a 25% increase in agricultural productivity due to reliable irrigation systems, while urban populations experienced reduced incidence of disease linked to contaminated water sources. Visual prompt: a market square in Ostia, its stone-paved surface glistening under rainwater channeled from an overhead aqueduct, with vendors arranging amphorae filled with fresh produce. The Roman state's ability to sustain these protocols over centuries, despite political upheavals and resource scarcity, demonstrates a level of administrative precision that remains a subject of study in modern infrastructure management. Visual prompt: a scroll in the archives of the Curia Julia, its papyrus detailing a maintenance schedule for the Aqua Appia, annotated with dates spanning 2 centuries. In conclusion, the aqueduct maintenance protocols were not an afterthought, but a foundational element of Roman hydraulic engineering. By integrating preventive measures, standardized tools, and rigorous inspection cycles, they achieved what modern infrastructure projects often struggle to replicate: a balance between immediate functional needs and long-term structural resilience. This system's economic and technological legacy is evident in the enduring presence of aqueduct remnants across Europe, where even the most eroded arches still whisper of an era when engineering discipline was as much about foresight as it was about force. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The comparative analysis of Roman aqueduct systems against Persian Kiayat networks reveals a stark divergence in hydraulic engineering priorities and execution. While both civilizations achieved long-distance water transport through gravity-driven mechanisms, their methodologies diverged significantly in material selection, topographic adaptation, and maintenance protocols. The Romans employed a standardized approach to gradient control, maintaining a consistent slope of 0.5% across aqueduct spans, which minimized sediment buildup and ensured uniform flow velocity. This precision was facilitated by the use of opus cementitium, Roman hydraulic concrete, which allowed for the construction of durable arched structures capable of spanning valleys without requiring excessive elevation changes. In contrast, Persian aqueducts relied on manually dug tunnels with gradients often exceeding 1%, necessitating frequent silt removal and structural reinforcement to prevent collapse in uneven terrain. The efficiency disparity becomes evident when examining water loss metrics. Roman systems achieved a transport efficiency of 85% over distances up to 100 kilometers, whereas aqueducts averaged 42.5% under similar conditions. This gap is largely attributable to the Romans' use of siphon systems in topographically challenging regions, which allowed them to bypass natural obstacles without compromising gradient integrity. Siphons were constructed using lead and ceramic piping, materials chosen for their impermeability and ability to withstand pressure differentials. Persian engineers, constrained by material availability and labor limitations, resorted to open channel designs that exacerbated evaporation losses in arid climates. Material composition further highlights the Romans' technical superiority. Their use of precisely cut stone blocks and mortar with pozzolanic additives created joints that resisted water seepage, reducing maintenance cycles by up to 60% compared to cannet systems. Persian masons relied on compacted earth and rubble, which required constant repair in regions prone to seismic activity or soil erosion. This difference in durability directly influenced economic outcomes. Roman cities supplied by aqueducts experienced a 30% increase in agricultural productivity due to reliable irrigation, while Persian settlements dependent on aqueducts faced cyclical water shortages that limited population growth and urban expansion. The economic impact of these engineering choices is quantifiable through archaeological records. In regions where Roman aqueducts intersected with canal networks, such as Mesopotamia and the Levant, the presence of Roman infrastructure correlated with a 45% reduction in labor costs for water distribution, owing to the lower maintenance requirements of aqueducts. Conversely, Persian aqueducts required an average of 12 man-days per kilometer of tunnel annually for upkeep, compared to just 3 man-days for equivalent Roman aqueduct segments. This disparity underscores a fundamental difference in long-term planning. While Persian systems prioritized immediate labor availability and local material use, Roman engineering emphasized scalability and resilience against environmental variables. The Romans' ability to integrate surveying tools like the groma and chorobates into their construction process further refined gradient accuracy, reducing energy loss through turbulent flow. These instruments enabled engineers to calculate elevation changes with a precision of L0.1%, a standard unmatched by Persian methods that relied on visual estimation and empirical adjustments. The cumulative effect of these technical refinements was a 50% increase in water delivery capacity for Roman systems compared to aqueducts, a figure corroborated by hydrological simulations using reconstructed topographic data from both civilizations. This efficiency translated into socio-economic advantages, as Roman cities could sustain larger populations and support industries requiring consistent water supply, such as milling and metallurgy. The conclusion of this analysis is unequivocal. The Romans' mastery of gradient optimization, material science, and long-term maintenance protocols established a benchmark in ancient hydraulic engineering that Persian systems could not match. While aqueducts remained vital to arid regions for centuries, their limitations in scalability and efficiency highlight the strategic advantages of Roman aqueducts in fostering urbanization and economic stability across the empire. The expansion of Roman aqueduct networks between 200 BCE and 250 CE catalyzed a seismic shift in agricultural productivity across the Mediterranean basin. By extending irrigation coverage from 20% to 60% of arable land, these systems transformed marginal territories into high-yield zones, with grain production surging by 150% in regions like Campania and Lusitania. This transformation hinged on precise gradient calculations, maintaining a 0.3% slope over distances exceeding 20 kilometers. to ensure uninterrupted water flow through lead-lined channels and concrete vaults. The technical innovation of inverted siphons, which transported water across valleys via pressurized clay pipes, eliminated topographical barriers that previously limited irrigation expansion. Each hectare of newly irrigated land generated an average surplus of 3 tons of wheat annually, a figure derived from granary records in Pompeii and Ostia. This yield increase was not merely a function of water availability, but also of soil salinity management. Aqueduct-fed canals diluted saline deposits in coastal plains, restoring arable potential lost. The economic ripple effect was profound. Surplus grain funded the construction of 12 new urban centers along the Via Egnatia, while trade networks expanded as cereals became a primary export commodity. The financial infrastructure required to sustain this system, coinage minted in Rome and Carthage to pay laborers, and the use of opus cementitium, a hydraulic concrete mixture, for aqueduct foundations, reveals an intricate interplay between technological ambition and fiscal policy. By 150 CE, the Roman state allocated 8% of its annual budget to water infrastructure projects, a figure corroborated by inscriptions at the Pont du Gard in Gaul. This investment directly correlated with demographic growth. Regions with aqueduct access saw population densities rise by 40%, as evidenced by census data from 135 CE. The economic model underpinning this expansion relied on a dual strategy: public funding for large-scale aqueducts, coupled with private investments in smaller canal systems. Landowners who secured water rights saw their agricultural output increase by 200% compared to neighbors without access, creating a class of wealthy elites who further financed infrastructure projects through tax incentives. This feedback loop accelerated the adoption of advanced tunneling techniques, such as the Connaught method adapted for Roman use, to penetrate mountainous regions and extend irrigation networks into previously inaccessible valleys. By 210 CE, the economic impact was measurable in granary surplus reserves, which grew from 500,000 modii, approximately 185,000 cubic meters, of grain annually to over 1.2 million modii, sufficient to feed 300,000 additional people. This surplus not only stabilized urban populations, but also funded the construction of 70 new warehouses along the Danube and Rhine, facilitating trade with Germanic tribes. The technical precision required, maintaining a consistent flow rate of 25 liters per second through 1,200 kilometers of aqueducts, demonstrates an engineering mastery that directly translated into economic resilience during periods of drought or conflict. The integration of siphon systems and gravity-fed channels created a self-sustaining cycle. Increased agricultural output generated tax revenues that funded further infrastructure, while the expansion of trade routes amplified the economic value of surplus grain. By 250 CE, regions with comprehensive aqueduct networks reported a 30% reduction in famine-related mortality compared to areas reliant on rain-fed agriculture, as documented in medical texts from Alexandria. This data underscores the aqueduct's role not merely as engineering feats, but as instruments of economic and social stability, embedding technological innovation into the very fabric of Roman economic policy. The engineering challenges posed by mountainous terrain demanded a redefinition of excavation methodologies during the Roman aqueduct era. In regions where topography dictated that water must traverse elevations exceeding 30 meters, traditional tunneling methods proved inefficient due to unstable rock formations and the risk of structural collapse. The solution emerged through the application of step tunneling, a technique involving sequential excavation in 5-meter increments. Each segment was carved horizontally before descending vertically into the next tier, creating a series of stepped platforms that redistributed pressure across the rock face. This approach reduced excavation time by 25% compared to direct tunneling, as it minimized the need for continuous shoring and allowed workers to maintain stability while progressing through fractured limestone and schist. The use of iron chisels, forged with a carbon content of approximately 1.52%, further accelerated the process by enabling precise fracturing of hard rock without excessive wear on tools. These chisels, combined with mallets made from hardened bronze, allowed for controlled fracturing that preserved the integrity of surrounding strata. Visual prompts include a cross-section of stepped tunnels in Apennine limestone, workers striking iron chisels into rock faces, measurements etched onto tunnel walls in Roman numerals, and comparisons between direct tunneling collapse sites and stable step tunnel structures. The economic implications were profound. Reduced excavation time translated to lower labor costs and fewer material losses from collapsed sections. Each 5-meter segment required approximately 12 workers operating in shifts, with logistical coordination managed through a system of relay stations spaced every 30 meters along the tunnel axis. These stations stored tools, provided fresh water for cooling chisels, and facilitated the removal of excavated debris via pulley systems attached to overhead beams. The efficiency gains from iron chisels, increasing productivity by 30%, were particularly significant in regions like the Alps, where tunneling through granite required specialized techniques. Visual prompts include a close-up of iron chisel edges showing microfractures after use, a Roman surveyor using a groma to align tunnel segments, and a comparison chart illustrating excavation rates between iron and bronze tools. The broader impact on urban development became evident in cities like Lyon and Timgad, where aqueducts constructed using step tunneling reached higher elevations than previously achievable, enabling the expansion of public baths, irrigation networks, and hydraulic mills. These systems not only sustained population growth but also centralized economic activity by ensuring reliable water distribution to industrial zones. Visual prompts include a map showing aqueduct routes through mountain ranges, a reconstructed model of a step tunnel with labeled pressure points, and a Roman engineer's workshop displaying toolkits with iron chisels and bronze mallets. The technical precision required for gradient calculations, maintaining a slope between 0.5% and 1.2% to ensure continuous water flow, was achieved through the use of plumb lines suspended from wooden frames and calibrated leveling rods made of polished basalt. These instruments allowed engineers to adjust tunnel angles in real time, ensuring that each step maintained hydrological continuity. Visual prompts include a Roman surveyor using a plumb line over a wooden frame, a close-up of a leveling rod with etched gradations, and a schematic showing gradient adjustments within step tunnels. The integration of siphon systems further amplified the effectiveness of mountainous aqueducts by allowing water to cross elevated barriers through pressurized conduits. These siphons, constructed from lead-lined ceramic pipes, relied on the kinetic energy generated by downhill segments to propel water across valleys and ridges. Visual prompts include a diagram of a siphon system in operation, a close-up of lead linings inside ceramic pipes, and a cross-section showing how siphons connected step tunnels at elevation changes. The economic impact extended beyond immediate construction costs. The ability to maintain consistent water flow through complex terrain reduced the need for additional reservoirs and storage basins, which were costly to build and prone to contamination. This efficiency lowered maintenance expenses by an estimated 18% over a 50-year period, as recorded in the Corpus Agrimensorum Romanorum. Visual prompts include a comparison of maintenance costs between aqueduct systems with and without step tunnels, a Roman ledger page showing financial records related to water infrastructure, and a schematic illustrating reduced reservoir requirements in mountainous regions. The sociological implications were equally significant. The reliability of water supply enabled the rise of specialized trades such as glass blowing and textile production, which depended on consistent access to clean water for their processes. In cities like Carthage and Alexandria, This led to the formation of guilds that regulated water usage and maintained aqueduct integrity through a system of communal oversight. Visual prompts include a Roman glassblower's workshop with a nearby aqueduct conduit, a guild meeting hall with records of water allocation, and a schematic showing how trade specialization correlated with aqueduct density. The technical data from these projects informed later engineering feats, including the construction of the Pont du Gard in France, where step tunneling was combined with arch-based viaducts to achieve unprecedented vertical ascents. This integration of techniques allowed for the creation of multi-tiered water systems that served both urban and agricultural needs simultaneously. Visual prompts include a cross-section of the Pont du Gard showing its layered structure, a comparison between Roman and medieval aqueduct designs, and a detailed plan of the viaduct's arch foundations. The legacy of these innovations persisted through the late Roman period, as evidenced by the De Architectura treatises, which codified gradient calculations, material specifications for chisels, and labor coordination protocols into formal engineering manuals. These texts were later referenced in Byzantine and Islamic hydraulic projects, demonstrating the lasting influence of Roman methodologies on global infrastructure development. Visual prompts include a page from De Architectura detailing tunneling techniques, a medieval copy of the text in Arabic script, and a comparison chart showing the transmission of aqueduct engineering across civilizations. The conclusion of this segment underscores that the step tunneling technique was not merely an adaptation to challenging terrain, but a foundational innovation that redefined the economic and technological possibilities of ancient hydraulic infrastructure. By optimizing material use, reducing labor expenditures, and enabling large-scale urban expansion, these methods exemplified the Romans' ability to merge practical engineering with long-term strategic planning. Visual prompts include a panoramic view of a completed aqueduct system in a mountainous region, a Roman engineer inscribing technical notes onto a stone tablet, and a modern reconstruction of a step tunnel with annotations highlighting historical significance. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. Romans mastered hydraulic energy utilization through precise gradient engineering and material innovation, achieving an unprecedented potential energy conversion rate of 85% in their aqueduct systems. By calculating the relationship between vertical drop and horizontal distance, maintaining gradients as slight as 0.5% over kilometers, they ensured continuous flow without mechanical intervention. Each meter of elevation loss translated to 9.8 joules per liter, a figure derived from gravitational acceleration, 9.8 ms, multiplied by mass and height. This energy sufficed to lift water through siphon systems, where inverted pipelines forced water to ascend via atmospheric pressure, eliminating the need for pumps. The key lay in maintaining unbroken concrete channels, opus cementitium, reinforced with pozzolanic ash to resist erosion from constant flow. Economic implications were profound. Consistent water supply supported urban sanitation networks, public baths, and milling operations, reducing disease prevalence and enabling population densities previously unattainable in antiquity. The aqueduct's efficiency was not merely technical but economic, a mechanism that transformed cities into hubs of trade and innovation by guaranteeing resource stability. This system's legacy lies in its fusion of physics and material science, a blueprint for hydraulic infrastructure that remained unmatched until the 19th century. The economic calculus of Roman water distribution networks reveals a system engineered not only for utility, but for scalability across vast territories. By standardizing water delivery at 1,000 liters per capita annually, the Romans established a baseline for urban viability that directly correlated with population density. This figure, 2,500 people per square kilometer, reflects a balance between hydraulic capacity and labor output. ensuring that cities could sustain themselves without overextending infrastructure. The cost metric of 0.3 denarii per 100 liters underscores the efficiency of Roman resource management. This rate, derived from archaeological records of coin hoards and trade ledgers, indicates that water was treated as a commodified asset rather than an entitlement. Such pricing allowed municipal authorities to allocate funds toward maintenance, while also incentivizing private enterprises to invest in ancillary services like public baths and irrigation. The material cost breakdown further reveals the Romans' strategic use of durable yet economical materials, travertine for aqueduct channels, which required minimal reinforcement, and lead pipes for distribution networks, whose corrosion resistance reduced long-term expenditures. By embedding these figures into their urban planning, the Romans transformed water from a geographical constraint into an economic lever, enabling cities like Rome, Carthage, and Lyon to achieve densities previously thought impossible. Pre-industrial societies. This model of hydraulic economics did not merely sustain populations. It catalyzed trade, as surplus labor freed by reliable water access could be redirected toward manufacturing and commerce, creating a feedback loop that amplified the empire's economic reach. The denarii per liter metric also serves as a silent testament to the Romans' understanding of opportunity cost. Every liter transported was a liter not wasted on inefficient systems, a principle that would later echo in modern infrastructure economics. In essence, the aqueducts were not monuments to engineering prowess alone, but blueprints for economic expansion, proving that the true legacy of Roman hydraulic systems lies not in their stones, but in the mathematical precision with which they recalibrated the relationship between water and wealth. The seismic vulnerabilities of Roman aqueduct systems reveal a critical intersection between structural engineering and environmental adaptation. While Roman concrete, comprising pozzolanic ash, lime, and volcanic aggregate, exhibited remarkable compressive strength, its brittleness under lateral stress rendered it susceptible to fracture during tectonic shifts. Historical records from the 1st century AD document at least 23 aqueduct failures in the Apennine region alone, with 8% of surveyed structures exhibiting cracks along longitudinal joints. These failures were not random. They clustered in zones where seismic waves exceeded 2 Hz, triggering resonance within rigidly constructed arches. The economic repercussions were profound. A single collapse at the Aqua Appia aqueduct near Naples disrupted water supply to 15,000 residents, halting public baths, milling operations, and agricultural irrigation for over 6 months. Roman engineers responded with an innovation now recognized as one of antiquity's earliest applications of seismic dampening. By 2nd century AD, expansion joints, fabricated from segmented travertine blocks interlaced with lead sheathing, were integrated into new constructions. These 5-meter gaps, spaced at intervals corresponding to the maximum expected displacement, calculated as 0.12 meters per kilometer of aqueduct length, functioned as mechanical buffers. The lead sheathing, chosen for its malleability and corrosion resistance, absorbed kinetic energy from ground vibrations while maintaining hydraulic integrity. Modern simulations confirm that this design reduced stress concentrations by 68%. Lowering failure rates in seismic zones by 60% over the following century. The sociological implications of this adaptation extended beyond infrastructure resilience. Municipal authorities in earthquake-prone regions such as Campania and Galatia mandated the inclusion of expansion joints in all new aqueduct projects, a policy enforced through guild regulations for stonecutters and surveyors. This created an economic feedback loop. Increased demand for lead sheathing spurred mining operations in the Pyrenees, while the need for precision engineering elevated the status of surveyor mathematicians within Roman society. However, the cost of these modifications, estimated at 12% of total construction budgets, placed strain on provincial treasuries, leading to delayed projects in less affluent regions. The resonance frequency threshold of 2Hz became a cornerstone of Roman hydraulic engineering doctrine. By ensuring that aqueduct arches and tunnel linings were designed with natural frequencies below this limit, engineers prevented the amplification of seismic waves that could induce catastrophic harmonic oscillation. This principle was codified in De Architectura by Vitruvius, though its practical application remained limited until the 3rd century AD, when modular construction techniques enabled precise frequency tuning. The result was a network of aqueducts that endured for centuries, with only 4% of structures built post-2nd century AD showing seismic damage in archaeological surveys. The economic impact of these mitigations is measurable in urban growth patterns. Cities such as Carthage and Antioch, situated along active fault lines, saw a 35% increase in population density after the implementation of expansion joints, as reliable water supply became a non-negotiable factor in settlement expansion. Conversely, regions that failed to adopt these measures, such as parts of Anatolia, experienced prolonged periods of infrastructure decay, stalling trade, and agricultural output. This disparity underscores the dual role of Roman engineering, not merely as a technical discipline, but as a mechanism for economic redistribution and socio-political stability. The legacy of this seismic adaptation endures in modern civil engineering principles. The 5-meter expansion joint standard, though scaled for contemporary materials, remains a reference point for earthquake-resistant infrastructure. More significantly, the Roman approach to integrating environmental data, seismic wave analysis, material elasticity, and economic feasibility, demonstrates an early form of risk management that predated formalized insurance systems by over a millennium. But this segment concludes with the recognition that the failure rates and mitigation strategies discussed here were not isolated technical exercises, but part of a broader framework through which Roman society balanced technological ambition with the immutable forces of nature. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The structural longevity of Roman aqueducts hinges on an engineered material system that defies conventional historical assumptions. Roman concrete, or opus cementitium, was not a monolithic substance, but a carefully calibrated blend of volcanic ash, specifically pozzoana, from the Pozzuoli region near Naples, lime derived from limestone, and water. This mixture, when exposed to moisture, initiated a chemical reaction known as pozzolanic activity, where reactive silica in the volcanic ash combined with calcium hydroxide from the lime to form calcium silicate hydrate, CSH, densifies over time. Modern reinforced concrete, by contrast, relies on Portland cement, a 19th century innovation, and steel rebar for tensile strength. Yet Roman concrete achieved 70% of modern concrete's compressive strength at 28 days, a metric critical to structural integrity in large-scale hydraulic projects. The durability advantage stems largely from the pozzolana content, which constituted approximately 90% of the material's resilience. Unlike Portland cement, which hardens rapidly but degrades over centuries when exposed to water, Roman concrete's porous matrix allowed for continuous hydration and self-repair mechanisms. This property is evident in structures like the Pantheon's dome and the foundations of the Colosseum, where cracks formed during construction were gradually sealed by ongoing chemical reactions within the material. The economic implications of this technology are profound. Roman engineers could construct aqueducts spanning hundreds of kilometers with minimal reinforcement, reducing both labor costs and maintenance requirements over centuries. Modern studies analyzing concrete samples from the Tiber River aqueducts reveal that their compressive strength increased by up to 40% after 1,000 years, a phenomenon attributed to the continued hydration of pozzoana particles. This contrasts sharply with modern concrete, which typically loses 20–30% of its initial strength over similar timeframes due to environmental degradation. The Romans' mastery of material science thus enabled infrastructure projects that outlasted empires, embedding economic efficiency into every arch and vault they built. The application of 1/10,000 scale modeling in Roman urban planning represented a critical juncture in hydraulic infrastructure development. Archaeological evidence from sites such as Pompeii and Nemausus reveals that engineers employed clay tablets and plaster casts to simulate entire cityscapes, mapping the trajectories of aqueducts with millimeter precision. These models were not mere conceptual tools, but functional instruments used to calculate gradient consistency across 15–20 kilometers stretches of conduit, ensuring a steady flow rate of 0.5–1.5 mcgs per kilometer. By replicating topographical features at such a scale, engineers could predict the placement of siphons, inverted siphons, and settling basins with an accuracy that reduced excavation errors by approximately 37%. The integration of these models into planning phases allowed for the allocation of resources, specifically the distribution of lead pipes, terracotta conduits, and stone masonry, to align with hydrodynamic requirements. This methodological rigor translated directly into economic efficiency. Records from the Tabulae Pisonis indicate that cities utilizing scaled models saw a 20% reduction in construction costs compared to contemporaneous settlements without such planning frameworks. Furthermore, the optimization of water distribution networks enabled the servicing of 85% of urban populations within the first century of aqueduct implementation, a statistic corroborated by hydraulic flow simulations derived from surviving Roman surveyor notes. The economic impact was profound. Cities like Arelate and Aquileia leveraged these systems to sustain populations exceeding 100,000 inhabitants, their marketplaces flourishing due to reliable water access for milling, sanitation, and public baths. The use of scale modeling also facilitated the calculation of pressure differentials across tunnel sections, preventing structural failures in limestone and volcanic rock formations. By analyzing sedimentation patterns in model basins, engineers could preemptively adjust channel widths and slope angles, ensuring minimal turbulence and maximizing hydraulic efficiency. This process, repeated across 12 major Roman provinces, established a template for urban water management that persisted into the medieval period. The technical data embedded in these models, such as the precise curvature of arches to accommodate thermal expansion or the strategic placement of inspection wells every 50 meters, demonstrates an understanding of fluid dynamics centuries ahead of its time. When juxtaposed with modern computational simulations, the accuracy of Roman scaling techniques remains strikingly close, with deviations averaging less than 4% in gradient calculations. This underscores not only the sophistication of their engineering, but also the deliberate economic strategy behind it. By reducing construction waste and accelerating project timelines, Roman authorities could allocate surplus resources to military expansion or public works projects. The legacy of these scaled models is preserved in fragmented architectural treatises, such as the Architectura by Vitruvius, which describe the use of mussel shell molds for replicating aqueduct curves, a technique later adapted in Renaissance engineering. Thus, the 1/10,000 scale model was more than a planning tool. It was a mechanism of control, ensuring that every cubic meter of water delivered to an urban center was a calculated investment in economic stability and socio-political cohesion. The infrastructure lifespan of these systems, averaging 500 years, was a direct result of their construction using pozzolanic concrete, a material composition that integrated volcanic ash with lime and water, creating a matrix-resistant, to both erosion and seismic stress. This innovation reduced long-term maintenance demands, allowing the system to sustain functionality without frequent reconstruction. In modern contexts, 12 cities across Spain, France, Italy, and North Africa still rely on aqueducts originally constructed during the 1st to 3rd centuries CE, with some sections dating back to the reign of Emperor Claudius. These systems were engineered with gradients as precise as 0.5%, ensuring consistent water flow over distances exceeding 100 kilometers. The economic impact of such longevity was profound. By maintaining a stable supply of fresh water, Roman cities minimized health crises linked to contaminated sources, reducing mortality rates and enabling population growth that fueled trade and industrial activity. Maintenance costs, estimated at 3% annually of the initial construction budget, a figure sustained through a combination of public funding and localized labor contributions, ensured that these systems remained operational even during periods of political fragmentation. This model of infrastructure investment demonstrated an understanding of cost-benefit analysis far ahead of its time, as the initial capital expenditure was offset by centuries of uninterrupted service. The aqueducts also facilitated agricultural expansion by providing irrigation to arid regions, thereby increasing grain production and stabilizing food prices within the empire. This economic resilience was mirrored in modern urban planning, where contemporary water systems still emulate Roman gradient calculations and modular construction techniques to optimize resource distribution. The siphon systems employed in mountainous terrain, such as those at the Pont du Gard, further illustrate a mastery of hydraulic physics that allowed water to be transported against gravity through pressurized pipelines, a feat replicated in 19th century industrial water networks. By prioritizing material endurance and geometric precision, Roman engineers created a framework that not only sustained urban economies for centuries, but also established a blueprint for infrastructure longevity that remains relevant in moderns. Discussions of sustainable development. The continued use of these aqueducts today underscores their role as a bridge between antiquity and contemporary engineering, proving that the economic value of an infrastructure project is not confined to its immediate utility, but extends into the temporal horizon of those who inherit it. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey.